So hi everyone, how you guys doing? First of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is another exciting channel by Unacademy, which is India's largest online learning platform for IIT JEE. On this channel, every concept of physics, chemistry, and maths are being taught to you completely in English. So this series is one that I host for class 12 students. Now, the topic that we are discussing right now is electromagnetic induction, and today we'll be talking about inductors and mutual inductance. So before we move forward, before we get started with today's discussion, let me introduce myself for those of you who might not know me. So my name is Rohit Dixit and I studied mechanical engineering from IIT Delhi. And for almost 8 years, I've been teaching physics for IIT JEE. And all this teaching so far had been offline, and offline I had been associated with some of the topmost institutes in the JEE industry. Now, I myself was already at rank 447 and All India rank 192, the two stages of the IIT JEE exam that I took. I also qualified NTSC Stage 2 as a student, and I was in the top 1% in the NSCP, which you better know as first stage of the Physics Olympiad. Now, I've already coached many students to great ranks, to some top ranks in the both JEE Mains and Advanced in the offline setups. Now, I hope to continue doing that here with you guys online. So, how can you guys make sure that you are getting cracking this exam, getting top ranks, and getting your dream colleges? So you can get yourselves the Unacademy subscription for that. This subscription will give you benefits like live classes where you get to interact with your educators on a regular basis. So these features ensure that your studies are going uninterrupted even in this lockdown, where you have no option but to study offline or online on any of the platforms. So Unacademy is one of the best platforms that you have there for your preparation. This will make sure that your studies go ahead in a planned manner, okay, and help you achieve your dream ranks. So these classrooms will also have live polls and leaderboards, which keep them highly interactive and quite fun. All right, so you also are a part of a test series and analysis. For a competitive exam like IIT JEE, it is very important to constantly keep self-assessing and know where you're lagging behind. So you have expert teachers here which will guide you to how to perform better and better in the examination. And of course, you have live doubt clearing sessions when all your Academy Plus courses. So, as a matter of policy, all the Unacademy courses have a live doubt clearing session as every fourth session. So, after every three teaching sessions, the fourth session is compulsorily a live doubt clearing session. So, with Unacademy Plus courses, the doubts, trust me, never pile up. Now, on top of all this, you are getting the opportunity to study from the best educators all across the India from the comfort and safety of your home. Next, so these are the ongoing plus courses by the J English team that are being taken for class 11 students. So even class 12 students or 2021 aspirants can join these if they want to master these concepts. There are three courses currently going, and this includes one course that I'm taking, which is an advanced course on mechanics. Then you have four more courses available for class 12 students or 2021 aspirants, including one advanced course on electromagnetism that I am taking. All right, so how do you enroll in these courses? How can you make sure that your studies are going better than others? So get yourselves the Unacademy app first. Once you have done that, go to the plus section of your app, select your goal as IIT and click on the get subscription button. Now, once you do that, you will be redirected to the payment page and where you will realize the pricing of the subscriptions has been kept very fair. And let me just show you the payment page so that you're aware of the subscription fees. Here it is. So you will realize when you are redirected to the payment page, you can use the code RDLive to get a 10% off on all your subscription fees, which are very reasonably priced in any case. So any reputed offline coaching would have charged you anywhere between 4 times to even 10 times in some cases to of this fees. So Unacademy is providing you an opportunity to study from the topmost educators and the same content you are getting online, the same personal guidance and at a very affordable price. So click on that proceed to pay button, enjoy a 10% off by using RD Live and give your JEE prep a huge boost. Now, Unacademy is also bringing you the Iconic subscription now. So Iconic subscription gives you a chance to take your JEE preparation to the next level with personal coaching. So here, with the Iconic subscription, you get a personal coach. You have IIT JEE workshops where experts give you guidelines. You have a study planner also. You have a regular test analysis, and you are giving personal attention, personal coaching. to get you to top ranks. So hello Amod, hello AP, hi Rajesh Amra, hi Aryan, how are you guys doing? So this is another way which you can achieve, which you can take to achieve your dream ranks. Okay. Now, okay, so announcement, new time for the Unacademy Combat Grand Finale. That is going to happen at 9 a.m. on 25th of November. So make sure that you attempt live and you can win some really cool prizes and scholarships. So you can enroll for free using the code RD Live again. And if you come first in this, so you will get prizes worth of 50,000 plus you get the Unacademy's 1 year subscription. Then for second rank, you get prizes worth 30,000 and also 1 year subscription of Unacademy. For third prize, you get prizes worth 30,000 and 1 year subscription of the Unacademy JEE subscription. For ranks 4 to 10 also, you will get 6-month Unacademy subscription and 25,000 worth of prizes. So compete in this exam live. Make sure you get those top ranks and win some really cool prizes. All right, so moving forward, those of you who are following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link. This will make sure that you are getting all the notifications of all these sessions and the amazing lectures that are happening here on the JEE English channel, and you won't miss out any of those. All right, so why don't we get started with today's discussion? So today, as I said, we will continue our discussion of inductors and we'll also talk about mutual inductance. In the last class, we had started the discussion over mutual inductance. We'll carry forward from there. So we had defined that mutual inductance involves interaction of one coil's magnetic field with another and results in induction of an EMF in one coil when the current through other coil is changed. Okay. Then we also realized that the the magnetic flux of one coil will be linked to the current of the first coil. Okay, like this, we can say that phi 2 would be directly proportional to phi 1, and we introduce a proportionality constant m, which is called the coefficient of mutual induction. And this you realize will have the same units as that of self inductance. It is Weber per ampere, which is given a special name Henry. Okay. Now we also realize that for a set of two coils, the coefficient of mutual induction is same for both the coils, whether you're talking about the flux linked to 1 due to the current in second, or due to the flux linked with 2 due to the current in 1. So this was known as reciprocity theorem, and we also realized that m is a scalar quantity and SI units, as I've already mentioned, is Henry. Okay, so let's move forward and let's see how we would calculate the coefficient of mutual induction, how you would go about that. So here is an example where you have been presented a situation where you have been told, consider the figure which shows two long coaxial solenoids, each of length L. Let the radius of the inner solenoid be R1 and the number of turns per unit length be N1. Now the corresponding quantities for the outer solenoid are R2 and N2. You have to calculate the mutual inductance coefficient M for these two concentric solenoids. So how do you do that? So you will go back to the definition that we know how we define M is that M can be defined as phi 2 over I1. Okay, so now, or you can also say it will be phi 1 over I2. So you send current in any one of the coils and you will realize that the mutual induction coefficient would be the flux linked to the second coil due to the current in one over the current. Okay, so it is the flux linked with one coil with respect to per unit current in the other. Okay, so let's see. So here you have two solenoids, right? So let's draw these two solenoids using two colors. So imagine this is a solenoid which has a radius R1. Okay. Again, we have been told to neglect the end effects, so we will still continue using the equation for infinite solenoids. Then you consider that you had another inside this, you had another small solenoid, this. So what we will try is we will solve for both the cases when the current is flowing in the outer solenoid and when the current is flowing in the inner solenoid. And then we will also realize that, yes, in fact, the M coefficient will come out to be the same. Okay? So let's imagine that initially the current I is flowing through the coil inside. Okay, so let's imagine that. that the current is flowing through here and some I1 current is flowing through here. I think the radius of this was R1. Okay, so radius of this, and I know the number of turns per unit length. This has a radius R1. The outer one has a radius of R2. Okay, and the number of turns per unit length in the inner one for N1. So N1 here and N2 for this one. Correct. So now I'll know that what is the magnetic field that is being produced by the inner solenoid. So as I said, we have been told to neglect the end effects. So I can treat this as an infinite solenoid. Correct. Hello, Mahiji. Good evening to you as well. How are you? So can I say that since B due to 1 would be mu naught N1 N and times I. Okay, so this is the flux that is being produced. So what will be phi 2? I will realize that phi 2 would be the N2. Okay, so N2 into L. So N2 being the total number of turns times B1 times the area in which this field is. Now the area that this field is going to be in L will be, that is going to be, you realize the area of the inner one, because the magnetic field lines will come here. Okay, so in what area are they spread? Will be spread in the area of the inner coil. Correct. Hello Divya, how are you? Hi Motilal. Good to see you here. Okay, so what class are you guys in? Motilal, what class are you in? So the area you realize would be pi r1 square. So do you agree that this is how I could have written N2? Okay, so sorry, phi 2, where N2 would be n small n2 times L, where L is the length of these solenoids. Okay, both these solenoids are of length L, which was given to us. Okay, and number of turns per unit length for the first for solenoid number 2 was N2. So total number of turns would be N2 times L. Okay, so if I use this formula, let's see what I'm getting. I'm getting that therefore phi 2 is, let's see what is phi 2. Phi 2 becomes B1, which is mu naught, then I have N1 and I have N2 and I have L times pi R1 square times I1. Okay, and the coefficient of mutual induction I know. So M would be equal to phi 2 over I1, which gets me mu naught N1 N2 pi R1 square times L. So this is the formula of the coefficient of mutual induction that I'm getting. Okay, so I hope you realize that what all factors is this depending on? This depends on the number of turns per unit length. So it is depending on the characteristics of both the solenoids, the dimensions of the inner one, okay, and you will realize the length of both the solenoids. Okay, so that is what you have here. Also, if I wanted to connect, if I wanted to think instead of this, if current was flowing through the outer one. So imagine if I2 current was flowing through the outer one, then how would have I calculated things? So let's say if I2 was sent to the outer solenoid, then let's see. Then I should get the same value for M. Let's check, are we getting it or not? Then you realize that the magnetic field that would have been produced in such a case, that would have been here, this entire region, right? And how much that magnetic field would have been? I will realize that magnetic field B2 would have been mu naught to N2 into I2. Correct? Okay, so you are in class 10th now. All right. So this is a series that is meant for class 12 students, Motilal. So are you already preparing? Have you already started preparing for IIT? From here you will realize phi 1 would have been equal to N1, which would be the total number of turns in solenoid number 1 times B2, okay, times area of one, which would be again pi r1 square. So you realize if you substitute the values here, again you will get the same answer. Mu naught n1 n2 by r2 square, r1 square only, because the area of the inner coil is by r1 square times L times I2. Okay, so you will realize M again is getting through, coming out to be the same. So again, I keep writing this R2 square, it will be R1 square only. Okay, so you do realize that yes, the M indeed comes out to be the same. It doesn't matter which coil the current is being sent to. Okay, the coefficient of mutual induction, as I said, from reciprocity theorem, you already knew that it will be same for both the coils. Okay, whether you send current in one and check out the flux in the second, or you send current through second and check out the flux in one. Okay, the reciprocity theorem says that the coefficient of mutual induction would be the same, which we can see also. So I hope everybody followed this. Okay, if you followed this, this is going to be the standard way of calculating the coefficient of mutual induction. So how do you do that? You imagine some current I1 in one coil, you find the flux linked to the second coil, phi2, in terms of I1, then you know M is calculated as phi2 over I1. Okay, so that is going to be the standard method of calculating the mutual induction coefficients. Quiz completed. No Papi ready today. Quiz I have planned at 8:30. Okay, because here the schedule would get congested, and plus I wanted to finish EMI today, so that is why I did not want to lose out on my session timing. Okay, so that is why this quiz today I have kept at 8:30. You guys can join me at 8:30 in night for the quiz. Okay, the quiz is going to be about magnetism and matter. All right. So no, you haven't missed the quiz. Don't worry. Let's go about this discussion first, though. Okay. So today we'll be trying to finish the discussion of EMI, so that from the next class we can start discussions of AC, alternating current. So let's look at another problem of calculating mutual induction coefficient. So here you've been told, consider this figure which has two concentric coils now. The inner one has a radius R2 and the outer one has a radius R1. The inner coil has turns, total number of turns capital N2. The outer one has total number of turns capital N1, and we want to calculate the mutual induction coefficient. Okay, why that chapter not there in reference books? So which chapter is not there in reference books? When it doesn't matter. Oh, it is there. It is there. Why is it not there? What are you saying? It is there. It's usually either clubbed in the magnetism chapter only, or given in some EMI chapter also at times. Okay, so that is definitely a part of your syllabus. It is there in NCRT. We are treating it as a separate topic. Okay, it is given in NCRT also, magnetism and matter. So we're going to be talking about all sorts of paramagnetic, ferromagnetic, diamagnetic substances and everything. How the polarization in them works. Okay, how they behave in different fields. This, as you know, in JEE 2020 Advanced, you had a very tricky problem about that. So that's a very important topic which is often neglected. I agree that often people tend to neglect that topic. So see, even you don't know that it is there in most of your reference books. It is there. You will find that topic even in your HCV, I think. So what are you saying? Hello Vishnu Dev, how are you? So let's try and see how we could have calculated the coefficient of mutual induction. Again, as I said, you can imagine the current flowing through any of the coils. So in this case, let's imagine that some I1 current is flowing through the outer coil. Okay. So let's assume I1 current flowing through the outer coil. Okay. Now, can I say, I know the magnetic field it will produce at its center, the outer coil, B at the center. So let's call that B1. I know how much that is. Mu naught over mu naught I1 over 2R1 Great. That is the formula. I hope you guys remember this. Now, you have been told why I'm calculating this for the center. You have been told that assume R1 is much, much greater than R2. So R2, though in this diagram it appears very big, you have to assume that R2 is very, very small. So I can assume that the R2 is so small that practically this is what you will see. Okay, so let's imagine that the outer coil would have appeared like this. So let's say this is the outer coil. Okay, and the inner coil is so small that it appears to be almost at the center only. Almost at the center. So for the entire area of the inner coil, I can assume the magnetic field to be almost uniform, which will be equal to this. Okay, so in this entire region, I can assume the magnetic field to be almost uniform. Okay, so here I forgot to multiply N1, which I definitely must. Okay, since there is not a one turn in this coil, there are N1 number of turns, so we needed to multiply with N1 also. Now, once I've calculated the magnetic field passing through the inner coil, now the flux linked to the inner coil is easy to see. What will be phi 2? Phi 2 would have been N2 times area of the inner coil, which would have been pi R2 square times V1. Correct? So, which tells me that phi 2 is, if I substitute the value of B1 like this, so I'm getting mu naught I1 I and mu1 I1 into N1 into so times N1 times N2 times pi R2 square, okay, over 2R1. Okay, so I also know M. What will be M? M would have been phi 2 over I1. So let's see how much M I am getting. I am getting this as my M. So you realize again, if you would have considered that the current is flowing through the inner coil, and then if you would have tried to calculate, it would have been the same for the outer one. Okay, so this is how you will calculate the coefficients of mutual induction. Standard approach: assume the current flowing through one coil, find out the flux or magnetic field it produces passing through the other coil, find out the flux length, and then flux length per unit current would be the coefficient of mutual induction. Okay. So if there are any confusions, you can let me know, by the way. Okay. Cool. Is it all clear? All right. So now let's move on to a very, very tricky problem that was asked in JEE Advanced. Okay. So this is a very tricky problem. One of I think I really like this problem. So I really if these are the kind of problems that IIT Advanced wants to ask of you. They want to see how much of the topic do you understand. So they asked you a question which appears to be a very, very tricky situation. Trust me, this question had confused a lot of students. That is why I wanted to discuss this in my lecture. So you have been told that a conducting loop of shape of a right angled triangle of height 10 centimeter is kept such that the 90-degree vertex is very close to the infinitely long conducting wire. You can see the figure. So there is an infinitely long wire and there is a right angled isosceles triangle. Okay. So which has been kept like that. The height of the triangle has been given to you. You have been told that the wire is electrically insulated from the loop, which means that when current is sent through this loop, it won't enter the wire. Okay, they're not touching each other, so you don't have to worry about that. They have been electrically insulated. Now the hypotenuse of the triangle is parallel to the wire, as you can see in the figure. The current in the triangular loop is in the counterclockwise direction and is increased at a constant rate of 10 amperes per second. Now, which of the following statements is correct? So A says the induced current in the wire is in the direction opposite to that of the current along the hypotenuse. Option B says that there would be repulsive force between the wire and the loop. Option C says that if the loop is rotated at a constant angular velocity about the wire, then the additional EMF of mu naught over pi volt is induced in the wire. Option D says that the magnitude of the induced EMF in the wire is mu naught over pi volt. So why don't you guys give this problem a try? This is a very, very tricky problem. So here is the situation. So you had an infinite wire here. You have a rectangular loop, a triangular loop here. The triangular loop seems to be carrying this current I, which is changing at a constant rate, and you've been told that di over dt is 10 amperes per second. So it is increasing at a rate of 10 amperes per second. Now, think about what effect will this current. So this loop would have produced some magnetic field, right? That magnetic field would have had some flux linked to this wire. Now, let's have a quick question. So this is an open wire. If this is an open wire, can I say that there is some flux linked with the wire? Can I say that? Can flux be linked with an open wire? Think about it. Fluxes are usually linked with closed loops, right? So how am I saying that, there is some flux linked with the open wire and that is producing a EMF? Yes, AP, this is a very, very tricky problem. See, this is a JEE advanced problem. The JEE advanced problems can be tough and tricky. Yes, absolutely. So advanced problem. If I remember the year correctly, I think this was asked in 2016. Okay, I think. So I don't remember the exact year, but it's definitely an advanced problem. So yes, it is going to be tough and tricky. Okay. So Suraj, okay, so Suraj is saying something. Suraj says Ampere circle law can only be applied in certain cases. Does it mean that the law is not true in general? No, Suraj. No, Suraj, you are wrong here. It is valid everywhere. It is useful only in some places, just like Gauss theorem. It can be applied everywhere. Okay. So who told when you are saying it can be applied to a certain cases, that just implies that that just implies that it can be applied usefully only in a few situations. Okay, it is always true. Okay, so it is always true. It is you will realize later that Ampere circle law is one of the is actually one of the Maxwell's equations, right? So Maxwell had described the entire theory of electromagnetism with four equations, which are called the fundamental equations of electromagnetism, right? So those are Maxwell's equations. Those are laws of nature. Those are always valid. Have absolutely no violations whatsoever. Okay, so you have got this slightly wrong, Suraj. It's not that I cannot apply Ampere circuit law. The point is that I cannot apply that usefully. Even if I try to use Ampere circuit law, that will not give me a productive result. Okay, so that's the difference. Okay. Okay, I hope you realize that. Okay. So is there a lag in the stream, by the way? Thank you, AP. So how about this problem? How about this problem? Try and work it out. Try and see if you can figure this one out. This is a very, very tricky situation. Okay, I can't seem to understand. Why is the stream slightly laggy? Hmm. Okay, so net is fluctuating a bit. All right. So any thoughts of how you would have solved this one? Day after tomorrow is your physics board exam. Okay, so early in November. So these are some odd timings for having board exams. Okay, is it any better? Is the stream any better? I have tried to slightly improve the settings. I don't know if that has much effect. See, the net speed at my end seems fine. So if now also there is some delay, I absolutely have no idea why that would be. Because the stream speed that I'm getting is super awesome. All right. So any thoughts on how you resolve this? First of all, could you figure out how can there be a flux linked with an open wire? Oh, in Nepal, but still. Okay, so do you have like a Jan to December session there? Okay, maybe. All right. All right. So how is a flux getting linked? How is the flux getting linked with an open wire? Let me know. All right. So first of all, let me tell you, this is an infinite wire. So an infinite wire can be considered to be a circular loop of infinite radius, right? So that is why you are getting flux linked with this wire. Okay. Now, how do I find the flux linked? If I can find the flux linked with the wire, then I can find the EMF induced. Okay. So the trick for that is if I can figure out the coefficient of mutual induction. So coefficient of mutual induction can be calculated using the fact that from the reciprocity theorem that if the current was flowing through the wire and I could calculate the flux through the loop, triangular loop, then the coefficient of mutual induction would have been the same. Okay, so that is going to be our trick for the analysis. Okay, so let's see. So we will first try to find the mutual inductance of the two coils. Now, if I can do that, then I can solve the problem easily. Okay. Now let's see that how we go about that. Okay. So as I said, the trick for that is that reciprocity theorem tells me that even if the current was flowing through the infinite wire, then the flux linked with the triangular loop can help me calculate the value of m, and m does not change. Okay. So that is the trick that we are going to use. I will imagine that this infinite wire is carrying some current I. Say this is carrying some current I1. Now, can I calculate the flux linked with the triangle? Think about it. Turns out, yes, I can. So this I know is 90. This height is 10 centimeter. This is 90. And this is an isosceles right angle triangle. Okay, which has not been mentioned but would be given. Okay, this is parallel to this. So first of all, we need to do that. So imagine this is 45. This is 45. So what we do is first we go to a distance x and we consider an element of thickness dx. Okay. Now at a distance x, I know what is the flux or what is the magnetic field created by the wire, right? Okay, so let's write that. I know here B at x, B at a distance x by an infinite wire. How much would that be? That would be mu naught I1 over 2 pi x. Okay, I hope you remember this formula. This rule says, is there any difference between beta particles and electrons obtained by thermionic emission and photoelectric effect? Okay, sir, take this question at last because I'm disturbing. Sorry, that's all right. That's all right, Sudhir. No, there is no difference. First of all, there is absolutely no difference. Beta particles are, in fact, electrons which are completely identical to the electrons that you have in any other process. Okay, so how about can I find the length of this? If I can find the length of this, so length obviously I can see. So for that, what I will do is I will find two triangles. I will use similarity to find the length. The first triangle I want to take is this one. Okay, and the second triangle that I want to consider is this. So let's consider this one. Let's consider these two triangles. Okay, so in these two triangles, they will be, first of all, uh, similar to each other, right? So the height of the smaller triangle is x, the height of the bigger triangle is 10, and you know that this is 90. So if this height is known, you already know the base. Okay, so what will be the base? So this is 45. So you realize if this is 10, this would also be 10, correct? Right? If I draw like this, then this is 45. This would also be 45. Okay, so I will realize that this will be equal to this. So this and this both are equal to 10 centimeters. So I know the base also. The base is 20. So from similarity equation between the two triangles, can I say that this length, let's call this L. So can I say x over L would be equal to 10 over 20? Okay, easy to see. So I can say that L equals 2 times x. The length of the portion in which the flux I will want to calculate is this. Okay, so now I know the length of this area. Let's use some darker color. I know the length of this segment. I know the width of this segment. So I can calculate the flux passing through this small area dA. Okay, so let's calculate that. So can I say that phi? What will be d phi? D phi would be b at x times L times x. Okay, we have ourselves a rectangular strip with a thickness dx and a length L. So this will be the flux passing through this rectangular strip, right? Okay, now all I need to do is integrate this to find the total flux. So I already know the total flux would be integral of this, where x will go from 0 to 10. So instead of 10, let's write 0.1 because let's stick to the SI units. Okay, see, so phi can be calculated. So I1, this is phi 2, phi linked with the triangle. What is phi 2? Phi 2 would be integral of, now B was mu naught I1 over pi 2 pi x times, let's see what is L. So L is 2x, so into 2x times dx. This 2x gets cancelled, and x you are varying from 0 to 0.1. So what you realize is that if you integrate, you are getting mu naught I1 over 10 pi. Agreed? This is the answer that you got for phi 2. Therefore, what is my m? M would be mu naught over 10 pi. This is the coefficient of mutual induction. Okay, I hope you guys followed things still here. That first I imagined that the current was flowing through the infinite wire. I tried to find out the flux that would get linked with the triangular loop due to this current. Okay, so this current would have produced some magnetic field, which would have caused some flux linkage with the triangle, which I can easily see. And then I calculated the coefficient of mutual induction by using the fact that M would be phi2 over I1. Correct? So this is the answer that we have got for the coefficient of mutual induction, first of all. Okay. Now, let's see what will happen when the current actually flows through. So let's add a page here. Now let's imagine the situation that was given to us. Okay, so now you know that this was the case that this is the wire and this triangular loop, this, and this triangular loop is carrying a current of some I2. Let's call this I2. Okay. Let's assume that this is carrying. Okay, so that I2 was in the counterclockwise direction. Okay. I2 was going through it like this. So this is the direction of I2. Now, this would have caused some flux linkage with the open-ended wire. How much flux would have been linked? I can calculate that. I can say that phi linked with 1 would have been m times I2, correct? So what would be d phi 1 over dt? Yes, d phi 1 over dt would have been m times di2 over dt. So let's see what we are getting at. The m was mu naught over 10 pi. Okay, so we are getting mu naught over 10 pi into the current was changing at a rate of 10. So mu naught over 10, mu naught over pi, that is the EMF induced. Okay, of course, I'll have a minus sign, which will essentially tell me about the direction. So EMF induced across the ends of the open-ended wire is in fact mu naught over pi. Now let's see the options that we have. So magnitude of induced EMF is this. Yes, this is correct. Now in this question, more than one was correct. Now let's try and figure out the direction of the induced current. What will be the direction of the induced current? Okay. So this is increasing, right? This current is increasing. In what direction is it producing the flux? It will be producing a flux which is coming out of the paper. Okay, so can I say this is producing a field which would be coming out of the paper? This, okay, okay, coming out. So yes, okay. No, we will have to redraw everything. No worries. Hmm. Okay, so coming out oh, is denoted like this. This is the direction of magnetic field, correct? So this is the magnetic field, and it is increasing, right? It's increasing. So the current in the wire would try to produce a field which is going downward. So for that, I already know that the direction of induced current would have to be in this direction. If the current flows in this direction, this would have produced a magnetic field going inside. So to counter the flux increasing, flux which is coming out of the plate from increasing, it will try to produce a flux which is going down. So which will be produced by this kind of current. So yes, first of all, you know that absolutely this is trying to tell you that yes, the direction of the current is same as the direction of current in the hypotenuse. Okay, so let's go back to our options, and what you will realize is that is what option number A says, that the induced current in the wire is opposite to the direction of current along the hypotenuse. No, that is wrong. So this is not correct. Now the second option says there is a repulsive force between the wire and the loop. Let's see if that is the case. So you will realize when the current starts to flow in both these. So first of all, you realize whatever force, so here you have to pay attention. Whatever force if this wire exerts on this wire, and whatever force it exerts on this wire, they will easily cancel each other out because the two directions are absolutely opposite. Okay, so the forces on these two wires will cancel out. The only force, the net force, would be the one that is being exerted on this wire. Now, these are two wires which are carrying current in the same direction. So I hope you know what do these wires do. The wires that carry current in the same direction. So what kind of force do they apply? They apply attractive forces, right? I hope you remember that. So the two wires, in fact, my infinite wire would have attracted the loop. Okay. So this is also false. Okay, this is also incorrect. That the force was not repulsive; it would have been attractive. Okay. Now, there is one option which also says if the loop is rotated at a constant angular speed about the wire. So imagine this situation. You have this triangular substance, okay, so it's this triangular loop, and this is the wire, and you're rotating it. Now, does the rotation of this loop change the flux linked to the wire? No, it doesn't. So if that doesn't, then there is no EMF induced. So this is also wrong. So there was only, in fact, one answer that was correct. So the option said that which of the following statements is or are correct. So we had to check all of them out. Turns out only option D is correct. Okay, I hope you figured out, you followed the entire solution. Let me know if you followed the entire solution, and if there was any part of this solution that you did not follow, you can let me know and I will go over that again. Okay, this again, as I said, is a very tricky problem. And imagining you facing such a tricky problem for the first time in the exam. Because usually in our practice also, I remember till that time, we wouldn't, we had probably never given such a question. Okay, so this is something new. So a lot of students panicked. So that is what happens if you know you're not keeping your concept strong. If you are just going after practice, if you think if I solve like 2,000 problems, I'll crack JEE. No, that doesn't happen. JEE will ask you a question which you have never seen before. So solving 2,000 problems will not help. Strong fundamentals and strong concepts will help. So if you knew how you could have approached this problem, if you could think at that time under pressure, imagine, then you would have done well. So let me know if you followed the solution here, and if there is any part of the solution that do not follow, you can let me know and I will explain that one more time. Okay? So trust me, JEE physics is very easy, but it's all about strong fundamentals and a decent amount of practice. Yeah, I'm not saying practice doesn't matter. Of course, practice matters. Of course, then only you will realize whether your fundamentals are strong or not. You have to practice as many questions as make you feel comfortable with the chapter, with all the concepts till the time you're feeling confident. But that is enough. You don't need to solve 2,000 problems or 1,000 problems or even 500 problems for every chapter. No, probably 150 to 200 problems every chapter are more than sufficient. I think 150 is also a very, very huge number. But still, if you want to cover the entire spectrum of boards and mains and advanced, then probably that kind of number is needed. Okay, so yes, all sorts of problems, including all these competitions. So for all these three competitions also, 150 problems per topic would be more than enough. Just make sure that you are getting your fundamentals strong and you're confident with your practice. Okay. So if there are no doubts in this question, tell me, I will move ahead. Okay. So let's move ahead and talk some more about the mutual inductance in terms of these self-inductances. So if L1 and L2 are the self-inductances of two coils kept close to each other, then the mutual inductance between the two coils can be represented as K times root of L1, L2, where K is called the coupling factor. And this coupling factor usually has a value between 0 to 1. Now, coupling factor depends on the orientation of the two coils and the separation between them. So if the two coils are very close to each other, or very far, so that, and how they're oriented. So maybe one is like this, one is like this, then the coupling factor would change. If both are parallel, then the coupling factor would change. So coupling factor depends on two essential components. One is the orientation, relative orientation of the two coils. Second is the relative separation of the two coils. Okay. Now, again, if there is absolutely no flux linkage, so if imagine I keep these two coils very very far away, so far that the magnetic field of one coil almost does not interact with the second coil, then the coupling factor automatically becomes zero. Coefficient of mutual inductance will become zero. And if suppose they are overlapping, if they're overlapping, in that case, all the flux linked with any one coil would be completely linked with the second coil. In that case, the coupling coefficient will become 1. Otherwise, its value practically would be between anywhere between 0 to 1. Okay, so this is the relation between uh, M, L1 and L2. So if you know all the three, you can find the coupling factor. If you know the coupling factor in L1 and L2, you can find M from there also. Okay. So let's take an example slightly later for that. So before that, we will talk about the combination of inductors. So let's talk about series combination. So when flux of the two inductors are in the same direction. Okay. So here we are assuming that there is some flux linkage of the two also. So mutual inductance is taken into consideration. So in the first part, we will say that M is non-zero. Mutual induction coefficient between them is non-zero. So this is the derivation for that. Now, what happens is that when you attach a battery of volt V, let's say like this, so I can write KVL equations. So let's write KVL equations, and for finding the equivalent, I always tell you how do you find the equivalents. You replace this by a single inductor, right? So you imagine the same amount of battery, the same volt battery should be connected to the same inductor or to a single inductor of L equivalent, and it should carry the same current. So if I current is here, the I current should also be here. And if di by dt in this circuit at any instant is present, then in this circuit also the same di by dt should be there. So the current, not only the current in both the circuits should be same, even the rate of change of current in both the circuits should be same. Then I can say that this inductor is equivalent to having these two inductors in series. Okay, so this can be called as equivalent of these two. If both I and di by dt in both the circuits are equal, okay, and of course the battery voltage is the same. So let's compare these two. So in circuit number 2, in let's call this the main circuit, circuit number 1. So let's apply KVL. So applying KVL, circuit 1. Let's see what we get. So let's start from here. So imagine if I start from here and I'm crossing the battery first. So if I'm crossing the battery first from the positive terminal to the negative terminal, the potential change would be plus V. Okay, so first term I can write as plus V. Now I'm crossing the inductor in the direction of the current. So when I cross an inductor in the direction of the current, what will be the change in potential? The change in potential would be minus L1 di 1 by dt. Okay, so here I have to also consider the total flux linked with L1. Now the total flux linked with L1 would be due to two factors. Okay, so that is what you need to realize. So one would be the flux due to its own magnetic field. Okay, so imagine this, its own magnetic field would be causing some flux passing through it. Try and draw that again. Let's say this guy is producing some magnetic field which will cause some flux linkage, and then the other adjacent one is also causing some flux linking. So both the coils are producing their own fluxes and the net flux in one. So what will be the net flux in one? Can I say? So first of all, let me write minus d phi 1 by dt. And similarly for the other one, I can write minus d phi 2 by dt. And this should be equal to 0. Okay. Finally, I will say what is the flux in coil number 1. That will be first the flux due to its own current, which will be L times I, plus the flux due to the adjacent coil, which will be M times I. Okay. Now we have already assumed that the flux in the two inductors is in the same direction. That is why we are adding. So they are coiled in the same manner. So one has clockwise coiling, so other also has clockwise coiling. So both of them will produce the fluxes or the magnetic fields in the same direction. So this is phi 1. Similarly, you can also write, what about phi 2? What is the flux linked with the second coil? Phi 2 would be, okay, so this will be L1I1. That will be L2I, which is the flux due to its own current, then Mi, which is the flux due to the current in the second one. So can I say here that V will be equal to di over dt times L1 plus L2 plus 2M. Okay. Now, how about for this circuit? For this circuit, I can say V should be equal to di by dt, okay, minus. So yeah, there will be, okay, yeah, V will be equal to plus I by dt times L equivalent. Okay, in the equivalent circuit, it will be like this. So what I can see from here is L equivalent would be L1 plus L2 plus 2M. Okay, I hope you guys can see that. Okay, now let's consider the other case. The other case is when the flux in the two inductors is in the opposite direction. So imagine if one coil is going like this and the other coil is going in the opposite direction. Okay, so that is the case. So one coil is coiled in the clockwise direction, imagine, and the other one in the counterclockwise direction. Then the magnetic field produced by both of them would be in the opposite directions, right? So one, let's say, if produces magnetic field like this, the other would have produced a magnetic field in the opposite direction. In the earlier case, both of them were producing the magnetic fields in the same direction. Okay, so yeah, I think here let's redraw. One was producing magnetic fields in this direction. The other is also producing magnetic fields in this same direction here. Okay. And in this case, they will be opposite. So the flux linked would in fact get subtracted. So in this particular case, what will happen? Phi 1 would be L1I minus, and similarly, phi 2 would be L2I minus Mi. Why? The flux produced by the adjacent coil is in the opposite direction of the flux produced by the coil itself. So in this case, what you will realize is L equivalent would be L1 plus L2 minus 2M. So I can say therefore L equivalent is L1 plus L2 plus minus 2M. Now plus or minus depends on whether they carry the current or they produce the magnetic field in the same direction or they produce magnetic fields in the opposite direction. So this is the formula. Now if M is ignored, if mutual induction is ignored, then the general formula for equivalent L, so let's write that also. So if suppose there were multiple coils, many coils, then you realize it's very difficult to keep track of all the mutual induction. Then what we do is we ignore that. So if mutual induction is ignored, so if mutual induction is ignored, then I can write that L equivalent equals summation of Li. This will be the formula for any number of inductors. Okay, that is the final form. So remember both of them. So this is for 2 where the mutual induction has not been ignored, and this is for any number of inductors connected in series where with mutual induction ignored. Okay, I hope everybody followed this. Okay. There is no confusion. If there is any part of the derivation that you did not follow, you can ask me and I will explain that. I will go over that one more time. To take a quick look of what we did. So we assumed the current, we calculated the flux through both the coils, then we applied KVL equation and compared it to the equivalent circuit which has been shown above. Okay, this is the equivalent circuit where the two inductors here have been replaced by a single inductor. Okay, so this is the equivalent circuit. Okay, so ARJ says cause we will get. Okay, so what ARJ saying? ARJ saying, sir, is it sensible to sacrifice means? I mean is cross the cutoffs like maybe 96, 97 percentile and then work for JEE Advanced because we will get 4 months more. So, in what sense? Are you saying that you won't complete the syllabus? Is that what you mean? That you are not trying to finish your syllabus in time for mains? See, because if you're covering the entire syllabus for advanced, then you're automatically prepared for mains. Okay, mains is just easier. You could have done the opposite way. If you're covering the entire syllabus, maybe you could have left the tougher problems aside and prepared only for slightly easier problems, and then yes, you would have prepared for mains and not prepared for advanced. But the opposite obviously cannot be true. If you are covering the entire syllabus, then you are automatically preparing for mains. Okay, the easy part already is covered, right? So if you're planning to leave out some topics, if that is what you mean, I don't know. I don't know. I never tried that, and I would never try that. I would rather plan it better than to have leave some topic to the end. Okay. So first, let me know what you mean, and then let me try and guide you. Okay. Again, now we will take a look at the parallel combination of inductors, and here again we will start and we will ignore the mutual inductance. Okay. So mutual inductance has been ignored. Let's write that here. Mutual inductance is ignored. Okay. So in general, also when you're having parallel combinations, so you realize in general also the flux linkage would be lesser. Okay, so that can also be ignored. What does flux in the same direction and the opposite direction mean? Okay, so that just means magnetic field lines are in the opposite direction or the same direction. Think about it. Think about it. Let's imagine that if you have the first coil, let's say you have the first coil, and here this has current flowing, coiling done like this. Okay, so the coils are going inward. Okay, let's imagine that. And the current here is going like this. So it is going from outer side to the inner side. Okay, that is how the current is flowing in this coil. And when you connect with the next coil, when you connect the next coil, I am doing the coiling in the opposite sense. In the opposite sense. Okay. So here the current is actually coming out. On the outer sides, it is coming out. Okay. So think of this. So where the current is going in, you realize what will be the direction of the magnetic field? The direction of the magnetic field produced here would be like this. Agreed. What about the direction of the magnetic field in the other one? Okay, so that will be in the opposite direction. Here the magnetic field lines are being produced like this. Okay. So now you see if this kind of flux, if the flux due to these magnetic field lines, see if flux due to these magnetic field lines gets linked here, it will be cancelling the flux of the self inductance. Okay, the mutual inductance flux causing the mutual inductance is essentially in the opposite direction to the flux that is causing the self inductance. That is what I mean. That the flux in one or created by mutual induction is in the opposite direction of the flux created by self induction. Okay. If the coiling were same, then both of them would have produced magnetic fields in the same direction. Okay, I hope you followed this. Is it clear now? Okay. So again, as I said, I am ignoring. All right. I'm ignoring the mutual inductance. Now I will imagine that a battery is being connected. Let's battery is connected, and the battery has a voltage V again. Okay, so V voltage and some current I is flowing, and I1 is going through inductor number one, I2 is going through inductor number two, and I3 is going through inductor number three. So can I say now that if I apply KVL, in one loop, then I'll get V equals L1 di1 by dt to be equal to L times di2 by dt times, which will be equal to L3 times I t by dt and so on. Correct? Now, for the equivalent circuit, I would have replaced everything with a single inductor, same battery, and a same current. Okay, and I can say L equivalent. So, for equivalent circuit, for circuit 1, I am getting this. For circuit 2, which is the equivalent circuit, this is for circuit 1. For circuit 2, I would have gotten L equals L equivalent times I over dt. Correct? Now, what you will also realize is that also I is equal to I1 plus I2 plus I3 and so on. Now, if I differentiate this equation, what do I get? I get therefore di by dt equals di1 by dt plus di2 by dt plus di3 by dt and so on. Correct? Now, from equation number one, from this set of equations in one, what I can say, okay, so let's start a page here. Let's move to the page from the first set of equations from one, I can say that di1 by dt would have been V over L1. Correct? I hope you can see that. di1 by dt would have been V over L1. Similarly, can I say di2 by dt would have been V over L2, di3 by dt would have been V over L3 and so on. And what do I get from the equivalent circuit? From 2, which is the equivalent circuit, I also get di by dt is V over L equivalent. Now all I need to do is substitute these values in the equation which I have here. Okay, so if I substitute all these values here, let's see what that gets me. That will get me, therefore, we can say that V over L equivalent is equal to V over L1 plus V over L2 and so on. So I'm getting 1 over L equivalent is equal to summation of 1 over Li. That is the formula that you're getting for parallel combination. So very easy to remember. These are exactly the same formula that you had for resistors. So for series resistors, you had this formula that equivalent is equal to summation of the individual inductors. So here, and again for parallel also, you are getting the exact same formula that you would have gotten for resistors. For parallel inductors, the equivalent inductance would be like this. So once you know how to calculate the net equivalent inductance, now you realize you can solve many problems of multiple inductors by replacing them by a single inductor. Okay. So all right, ARJ says, then why do they say it is better to give the first attempt Jan, then advance? It is better to take the April attempt. Then as after April there will be only 1 month left. Okay, so first of all, it is always better to finish your syllabus by it is always better to finish your NCRT plus main syllabus at least by Jan, so that you are also prepared for your boards, ARJ. So that is the first reason that you should be aiming for the Jan attempt, because when you're preparing for Jan attempt, your boards are already getting prepared along with that. Okay, so that's the first advantage I'll tell you. Second is, once you give that exam and you do well there, then you can focus entirely on advance. So that is the second advantage. Okay. But those are the two advantages when you should have planned things better. Okay. Third advantage that you get is, by chance, if something goes wrong in the Jan attempt, then you have yourself another chance, right? You already have an April attempt, where if by chance something goes wrong, if you made some mistake, if something happens which you couldn't control, then you can improve in the April attempt. So there are distinct advantages to taking the mains in Jan. Okay, definitely. I hope you got that. But then for that you need to plan things better. If you are still not, anywhere in finishing your preparation, then I would advise it's better that uh, it's completely up to you. So there are two methods still. So either right now you focus only on the boards and the JEE mains syllabus, take the JEE mains, then yes, the problem would be that you will be left with slightly lesser amount of time for advance. Okay, otherwise you should have already finished everything, and you could have uh, practiced some more of advanced problems in the last few months. Okay, so that would have been the ideal situation. Now there are still two options that you have. One is that quickly wrap up the NCRT and try and take the Jan attempt, then try and improve that in April, and also side by side prepare for advance. Okay, so that is one way that you can tackle it. Second way would be, okay, you keep preparing for your advance. You do not either take the Jan attempt at all, or you can take it, but don't take it too seriously. Okay, focus mainly on the April attempt, and make sure that you are preparing well enough for that, very well, and also preparing for advance. So these are two options that I can give you. That is the best case situations solution that I can offer you. Rest again, if you can figure out a better way, go for it. Okay, that is going to be my suggestion. Okay, so I would advise that take extra time, finish your NCRT, finish your HCV. That's it. Don't do anything else. Just finish NCRT, HCV, and previous year mains papers. That's it. That will be good enough. Trust me. For cracking mains, that will be good enough. So you do these three things, but yes, you have only 2 months left. So I don't know how much of that you will be able to manage. If you can, then well and good. Still try and go for that. Okay. All right. Coming to some questions. So on a cylindrical rod, two coils are wound one above the other, and you've been told what is the mutual induction if the inductances of each of the coils is zero point 0.1. So this is a very standard question, a very easy question. Again, a typical means level question. They will never ask you such an easy question in advance. So let's see how you would have solved this. Oh, very easy. So what does it say? On a cylinder, two rods have been wound one above the other. So if that is the case, then you realize that the flux linkage of one coil would be completely flux of one coil would be completely linked with the flux of the second coil. Okay, or the magnetic field would be completely passing through both the coils. Okay, so if you are taking a cylinder and you are taking two coils, go one over the other. Here is your one coil, and let's see, here is other coil. So you realize there will be complete flux linkage. Since there is complete flux linkage, so the K would be 1. Okay, so in the given situation, K will be 1 as the flux of both will be linked completely, right? As fluxes of both coils will be completely linked. Once I know K is 1, I immediately know M. What would that be? M equals K root. So both L1 and L2 were zero point 0.1 Henry only. So M would come out to be point. That's it. That is how easily you can solve. Yes, absolutely, Suraj. Very well done. Great. So here, let's try another problem. Another quick problem. Hello, Asharani. So, sir, can we do physics galaxy for JEE advanced problems? Okay, so Asharani, you can definitely do physics galaxy, but most of the problems of physics galaxy are actually meant for Olympiads. So you can leave out that they have another section which is the Olympiad section. But even in their regular question bank, even in their normal question bank, I've seen the problems are way too complex. They don't ask such complex problems in advance also. Okay, so I think you can definitely do it if you're feeling confident about your preparation and if you are ready for that level. If you have already practiced a lot and if you want to tackle some really challenging problems. But most of the problems of that book would be slightly more complicated even for advance. Okay, for Olympiads, it's a great book. So that is what I personally feel. Okay, I've seen the kind of questions. Trust me, most of the times J Advanced doesn't ask so many complex questions. Okay, so in my experience, sometimes that book just ends up demotivating the students a bit. So that if you can take care of that, if you know that, okay, so I'm just trying to take on something really challenging. It may or may not work out. If you're ready for that, if you can handle that mental challenge, then of course. Which do I prefer? So okay, so for advanced, I don't know. For advanced, that is the problem. There is no good book that I have found so far. Okay, I don't find any place to have very adequate collection of problems. Either problems are not up to the mark, or problems tend to be tougher only. So you have to manage with what you have. So first of all, as I said, previous year questions and HCV, those are the must. And then you can, depending on the level of your preparation, get more practice. Okay. So you can definitely try that. Okay, Physics Galaxy, it's an okay book. You could have, I don't know. You can also try problems from University Physics and Resnick and stuff like that. Okay, I think those problems are pretty decent. Problems in Resnick are pretty decent. Okay, so you could have tried those. Even University Physics, you could have tried. Otherwise, I'm not really sure. There is no one book which would have all problems which are consistent at the JEE level. There are a lot of books. So when we guys make our assignments, we refer to like a lot of books to give you that optimum quality of question. Okay, so no, those books I don't like. Uh, no, I don't find the questions level of questions very appropriate in the first one. I don't find that the questions are very good. And for the second one, it has a lot of errors, so it may end up confusing you more. Okay, so I don't like those books much. Yeah, I mean, instead of those, you should rather try Physics Galaxy. Okay, but then keep in mind that a lot of problems from that are way more complex. So try those, challenge yourself. Let's see. Okay. So here is another practice problem for you. This says a solenoid has 2,000 turns wound over a length of zero point 0.3 meters. The area of cross section is 1.2 into 10 to the power minus 3 meters square. Around its central section, you have another coil of 300 coils turns, which is closely wound. Okay. If an initial current of 2 ampere is reversed in 0.25 seconds, find the EMF induced in this coil. Okay, so let's see. This is a mutual induction question. Okay, so why don't we do one thing? So let's give this to you as homework, because there was still a small thing that I wanted to discuss before I end today's session, so that we can leave all the theory part also covered. So here is a question that you can do for homework, and this is another question. This is another question that was asked in JEE Advanced, by the way. Okay, so I think Asharani, the most wonderful thing is the previous year advanced problems only. Nothing can match that. So as I said, no matter how many books I see, either the questions are not up to the mark or the questions become way too difficult. Okay, so people have not been able to achieve a balance or reach that exact level where the advanced problems are. So like this one, this is not too difficult, not too easy. So somewhere which tests your understanding very well without making it too complicated mathematically. So I've seen what most of the authors they do when they are trying to get you tough problems. They make it mathematically more challenging, but that's not the idea. The idea is to test your concepts. Okay, so I don't like those questions, which will just have long integrations, weird maybe integration by parts, and different other aspects of mathematics. That's not what a JEE wants to. Okay, in any case, so here is another question. This was asked in JEE Advanced. So again, advanced question. So, however, very easy question, this one. Okay, so you can try this also. So two inductors, L1 which has inductance of 1 millihenry and a resistance of 3 ohm, and L2 which has inductance of 2 millihenry and a resistance of 4 ohm, and the resistance of 12 ohm are all connected in parallel with a 5-volt battery. Okay, now the circuit is switched on at a time t equals 0 to find the ratio of the maximum current to the minimum current. So this is very easy. So I will just tell you the hint and you can solve this later. You have this situation, okay, and this situation, and then this. So this is 12. This has an internal resistance of 3, and this has an internal resistance of 4. Okay, so at t equals 0, what will be the situation? At t equals 0, you will realize that will be current flowing through here and here. All the current flowing would go like this, right? Through the inductors at t equals 0, there can be no current passing. This will be I minimum. Why? Because at this stage, the resistance of the circuit will be the highest. Okay, so this is I min to be at t equals z. Next, at steady state, all these inductors will simply behave as resistors. Okay? So then you would have had current flowing through all three. Okay, and here you would have had I max, which would be at t equals infinity. So you know at infinity, the inductor would behave like a simply a resistor of 2 ohm, 3 ohm, and 4 ohm. So finally, you will have three resistances of 4, 3, and 12 ohms in parallel. In the initial condition, you have only one resistance of 12 ohms. Find the currents of two circuits, two stages, and find the ratio. This is how easy it gets. Okay. Yes, so here is another important part that I wanted to discuss, LC oscillations. So let's quickly go over that. So what you have is a typical circuit which has an inductor and a capacitor. Now, initially what you will do is you will connect it to position number 1. You will charge this circuit. Okay, so and I will assume that the maximum charge on the capacitor is capital Q. So let the maximum charge, write a little bit thinner, charge on the capacitor be capital Q naught. Okay, so I first uh, make this switch to position, shift it to position number 1. Assume that this guy gets a plus Q naught charge, this guy gets a minus Q naught charge. Now I shift it to position number 2. Now when I shift it to position number 2, the uh, the capacitor will start to discharge. Okay, and let's assume after some time to let let the charge on the capacitor, let the charge on the capacitor at time t be some small q. Okay, so I'm assuming in some time it has a discharge bit. Okay, so after some time it has discharge, it will be discharging like this. And let's assume that at this instant the current is small I. It is changing at a rate of di over dt. and the current, the charge here is plus q, and then here is minus q. So imagine at time, some time t, this is the situation of the circuit. Okay, so let the charge on the capacitor at time t be small q, and the current in the circuit, and the current in the circuit is in circuit 2. So circuit is in position number 2. Circuit 2 be small I changing at a rate I by dt. Now all I need to do is we will apply KVL. Okay, so let's see what applying KVL tells me. Applying KVL. Let's see what I can see. So look at this circuit number 2. First, we are going to go and cross the capacitor, and let's get started from here. So I am crossing the capacitor from its negative plate to its positive plate. So what is the changing potential? It will be plus q over plus q over c. Great. Now, when I cross this inductor in the direction of the current, the change in potential would be minus L di by dt. Correct? So I will write minus L di over d. This would be equal to 0, right? Now, one small little thing, I can also say Q by C is equal to L di over dt. Now, I will also realize the moment some di current is flowing in small time dt, you realize it will get a positive charge of dq here, which will reduce this, charge, or a dq charge would have flown from here, so this q would have gotten less. Okay, so dq dash that would have taken away the charge. So since the charge has been taken away, so I can say that I equals minus dq by dt. Okay, why the minus sign? Because the charge is being taken away from the capacitor. So as the current is flowing, the charge in the capacitor is actually reducing. Okay. So since I was minus dq by dt, di by dt, I over dt can be written as minus 2q over dt. Now all I need to do is substitute this value of I over here. Therefore, what I get is d2q over 2 equals minus q over LC. Now, does that equation look familiar? Yes, it does. This is the SHM equation. So, same as d2x by d equals minus omega square x. And I already know the solution of this equation, right? What is the solution of this equation? I already know. Here, omega would be 1 by root of LC. Okay, and what would be this charge equation? Charge would be q times capital Q naught sine of, that is the amplitude, that is the maximum charge that can come here. Okay, and you would have had omega p plus some phi naught is the initial phase, and I know since at t equals 0, q was equal to q naught, so I realize that phi naught would be pi by 2. Okay, so therefore the equation that I'm getting for charge is q naught cos of omega, or I can also write q naught cos of over root LC. So you realize that is why this is called an LC oscillation circuit. The charge will oscillate on the capacitor. Okay. Now, what is happening as the charge is oscillating? You will realize if you look at the equation of current, so that is the same as the equation of velocity, right? So current in the circuit I, let's see how does that vary. Will vary as not over root LC times sine of over C. Okay, because I was minus dq by dt. So minus dq by dt would have given me this. This is minus dq over dt. You realize at t equals 0, the current is 0, and then it grows to a maximum of q naught over root LC, and then it also oscillates sinusoidally. Okay, so I hope you realize if I made a graph, and on one axis if I kept q, so q would vary like this, oscillates this, and how about I oscillates like this. The variation of q, and this is the variation of I with respect to the variation of 2t. You have current and charge in the circuit, both are oscillating in fact. Okay, and that is why we call this LC oscillations. If you talk about the energy, so let's see what is the situation. So this diagram paints it beautifully. So initially you have all the charge is stored, which is the Q max in the capacitor. Now as the capacitor discharges, the current flows, and you realize that the energy is getting shifted from here. So you realize initially the energy was here in form of electrical energy stored in electrical fields. This energy from electrical fields is getting transferred to the energy that will be stored here in magnetic fields. Slowly, the entire energy that was stored initially in form of electrical fields would have gotten and stored here. The complete energy would have gotten from here to here, and then it would go back. So energy, just like in SHM, imagine you can draw an analog with the SHM also. Imagine this situation where a block is connected to a spring and it is oscillating like this. So you realize the energy, kinetic energy of the block is going into the potential energy of the spring, and then that potential energy comes back to the kinetic energy, and this oscillation keeps on happening. Similarly, in an LC oscillation, the energy stored in the capacitor, which is in electrical form, gets converted into the magnetic field's energy, and then this gets converted back into the electric field's energy. So energy is oscillating from the electric field energy to magnetic field energy, and so on. So that is what happens in LC oscillations. Okay. And now, quickly, I just want to mention about eddy currents also. This is the last thing that we will be discussing today. Eddy currents are loops of electrical currents induced within the conductors by a changing magnetic field in the conductor according to Faraday's law of induction. Okay, so imagine this is what is happening. So you have a conducting material, and over it you had, imagine, kept a loop which is carrying variable current. So this loop would have been creating its magnetic field. This magnetic field is increasing, let's say. This increasing magnetic field would have caused an induction of circular current loops in the material, which would have tried to create such a magnetic field which would try to oppose the flux change. Okay, I hope you realize that. These are what are called eddy currents, the currents that are producing this kind of flux, which will oppose the change in flux. I hope you realize when the conductor, you are increasing the flux going inside, so it will try to create its own flux which is coming outside. So this induction of circular currents, these are known as eddy currents. Now I hope you know what eddies are. Eddy or vortex is when water is rotating like this. Okay, this is called vortex. So if you see an eddy of water, so water is circulating like this. So these circulating currents are called eddy currents. Eddy currents flow in closed loops in conductors in the planes which are perpendicular to the magnetic field. Now, by Lenz's law, the eddy current creates a magnetic field that opposes the change in the magnetic field that created it. So whenever you have a surface of a conductor like this, if magnetic field is passing through this, and if this magnetic field starts to change, then it induces circular electric field lines. These circular electric field lines cause circular currents flowing through this conductor. These circular currents, which seem to appear out of nowhere, this is because of the induced electric field. They are called eddy currents. They will oppose the flux change that was causing them. So if such an increasing flux is causing this induction, then the current will be such that it will produce an outward magnetic field and vice versa. Okay, so that is all that I wanted to tell you about the eddy currents also. Okay, and thus eddy currents react back to the source of magnetic field. So there are a lot of applications of eddy currents which we can talk some other time. So with that, I would like to wrap up today's session. And before I go, let me remind you that this is how you should be getting your Unacademy subscriptions if you haven't gotten them already. Go to the plus section of your app, select your goal as IIT JEE and click on that Get Subscription button. Now, you will be redirected to the payment page where you can use the code RDLIVE to get yourselves the subscription and enjoy a 10% off on already very, very competitive pricing. Okay. Now, when you get your subscriptions, you can enroll in these courses which are already ongoing on the Plus app by the JEE English team. So there are 3 courses for class 11th, 4 courses for class 12th. So make sure you're getting your subscriptions and enrolling in these courses and giving your JEE preparation a huge boost. If you like today's video, then don't forget to press that like button, which already a lot of you have done. But another thing which I think most of you don't do is that you don't share these videos with others. So trust me, this is very high quality content which is being provided to you absolutely free for those students who can't afford these subscriptions. Unacademy wants to make sure that every student should have a right to quality education. So don't be selfish. Make sure that most of your friends are getting this opportunity to study quality content absolutely free of cost. So share it with as many people as you can. And trust me, doing good never hurts. Okay. Again, so don't forget to press the bell icon and the PDF notes of the slides used in today's lecture will be available for download very soon. And okay, so yes, this let me remind you that this has been shifted, right? So this is now happening earlier, and I've already shown you the slide. So go to that, make sure you are playing the final round of that, and win yourself some cool prizes. Again, those of you following on the JEE English channel can connect with us on the Telegram app using this link in order to receive all the notifications of all the sessions and lectures happening on the JEE English channel. Finally, this is my code RD Live. Use this code to get your subscriptions and